Hello students, myself Antara Ghoshal, Assistant Professor of EC Department of Guru Nanak Institute of Technology, and this is my lecture 27 and under the subject solid state device, and the code is EC301, and this lecture is under the module 4, that is field effect transistor. And under this module today we will discuss about a topic which is on the threshold voltage of ideal MOSFET. The subject name is solid state device and the code is EC301, and the total lectures of these subjects are 36, and there are some course outcomes. 4 course outcomes are there. First one is able to understand the energy band diagram, charge carrier transport phenomenon, and recombination generation process of different types of semiconductor materials. And second course outcome is able to understand the characteristics and current flow of semiconductor devices like BJT, JFET, MOSFET, and metal semiconductor junction and heterojunction devices. And the third course outcome is able to analyze the design parameters of MOSFET, that is channel length and width, depletion width, surface field and potential, on resistance, transconductance, equivalent circuits, amplification factors, capacitances, noise margins, scaling, and short channel effects of MOSFET. And the fourth course outcome is able to illustrate rectifying properties of different types of junction diode and importance of reverse current in solar cell and light emitting diode. Now, today's topic is the threshold voltage of ideal MOSFET, and for that today's course outcome is third number of course outcome, and this is the module 4, that is field effect transistor. Under this module there are two different types of topics. Main is junction field effect transistor, that is JFET, and metal oxide field effect transistor, that is MOSFET. And under JFET there was construction, field control, action and characteristics, pinch of voltage derivation, and some numerical problems. And under metal oxide field effect transistor, that is MOSFET, there are different types of MOSFET, structure of MOSFET. MOSFET means enhancement mode MOSFET, and the structure of MOS, the working principle of enhancement mode MOSFET with the characteristics, and also the drain current equation for linear and saturation region with condition. And there are many other topics, and the total lectures are 9 for this module. Now today we will discuss about threshold voltage of MOSFET, ideal MOSFET. That threshold voltage, which is defined as the applied gate voltage for requirement of achieving the threshold inversion point. Now the threshold inversion point, that is defined as the condition when the surface potential is phi s equal to 2 Fp for p type of semiconductor, and phi s equal to 2 phi Fn for n type of semiconductor. Already both these structures here, there are two structures which I have already discussed in previous lectures, so all of you know about these structures. Now these conditions which are shown in this figure, that phi s equal to 2 phi p, and for p type of semiconductor, and phi s equal to 2 phi fn for n type of semiconductor at the when the threshold inversion point is considered. Now this threshold voltage will be derived in terms of electrical and geometrical properties of MOS capacitor, means metal oxide semiconductor capacitor. Already I have discussed about what is MOS capacitor in previous lecture. Now this figure shows the charge distribution through the MOS device, that metal oxide, and here I am considering the P type of semiconductor at the threshold inversion point for P type of semiconductor substrate. Now the space charge width has reached its maximum value. Now we will assume that there is an equivalent oxide charge, that is Q bar SS, Q bar SS, and the positive charge on the metal gate at threshold is Q bar MT, and this prime indicates Q dash or prime. That prime indicates the charge terms, that indicates the charge per unit area. Even though we are assuming that the surface has been inverted, we will neglect the inversion layer charge at the threshold inversion point. Now from the conservation of charge, we can write that Q prime MT plus Q bar SS equal to mod of Q prime SD max, and where this Q prime SD max equal to ENA x dt. Here the charge is shown in this figure, that what is Q prime SD max, that is ENA x df dt, sorry, ex dt. And this is the magnitude of the maximum space charge density per unit area of the depletion region. Now the energy band diagram of the MOS system with an applied positive gate voltage, which is shown in this figure. Now already I have mentioned that an applied gate voltage will change the voltage across the oxide and will change the surface potential. Now in previous lecture I have already discussed about this equation, that Vg equal to del Vm plus del phi s. Vg plus del Vox, sorry, that is Vox, that is oxide layer voltage. Vox plus del phi s, that phi is means that is the work function of either S means semiconductor, if it is M then for metal. Now that is equal to Vox plus phi s plus phi ms. Now if we consider the threshold condition, then Vg equal to Vtn, that Vtn is the threshold voltage that creates the electron inversion layer charge. Now the surface potential, that is phi s equal to 2 phi 2 fp at the threshold, which I have already told in previous slide. Now this Vtn equal to Voxt plus 2 phi Fp plus phi ms, and that is Vtn equal to Vox T plus 2 phi Fp plus phi ms. That Voxt, that is the voltage across the oxide at this threshold inversion point. Now this voltage, that is Voxt, which can be related to the charge on the metal and to the oxide capacitance by like this, that Voxt equal to Q prime mt by COX. That COX is the oxide capacitance per unit area. And now we can write that if Voxt, that is equal to Q prime mt by COX, from this equation we can write that is equal to 1 by COX equal to, from this equation we can write that QMT prime equal to this minus this. We can write that Voxt equal to Q prime MT by COX equal to 1 by COX within bracket mod of Q prime SD max minus Q prime SS. Now, finally, the threshold voltage can be written as Vtn equal to mod of Q prime SD max by COX minus Q prime SS by COX plus phi ms plus 2 phi Fp. That is the threshold voltage. Finally, we can write the threshold voltage equation like this. This is the threshold voltage of an ideal MOSFET. Now, next come to the MOSFET capacitance. Now, what is the importance of this lecture? Now, uh, we will use these MOSFETs to design our circuits. Now, MOSFET capacitance tend to limit the frequency response of the circuits. In order to predict the circuit frequency response, we need to estimate the circuit capacitance. That's why we need to know about what is MOSFET capacitance. Now, we may use the MOSFET capacitance to our advantage. Now, what are the MOSFET capacitance? That MOSFET parasitic capacitance are divided into two general categories like extrinsic capacitance and intrinsic capacitance. And these extrinsic capacitance are associated with the regions of the transistor outside this dashed line. Means outside of this dashed line, there are extrinsic capacitance, and within the boxed region, there are intrinsic capacitances. All of these capacitances are under this box are intrinsic capacitances. Now, what are the different types of extrinsic capacitance, which is shown in this figure? That overlap capacitances, and these extrinsic capacitances are modeled by using lumped capacitance. And one capacitor is used between each pair of transistor terminals, plus an additional capacitors between the well and the bulk of if the transistor is fabricated on a well. Now, different types of extrinsic capacitance, like first one is overlap capacitance, that are mostly dependent on geometry. And also there are another type of extrinsic capacitances. Now, under these overlap capacitances, there are gate overlap capacitances. There are some overlaps between the gate and the source, which is shown in this figure. And also gate and source, and also gate and the drain. And there are some overlaps, and this overlap area gives rise to the gate overlap capacitances. The overlap between the gate and the source, gate and the source, and the drain, which gives rise to these gate overlap capacitances, which is denoted by that CGS O and GD 0 for the gate to source, 0, not 0, that CGA, that is gate to source capacitances overlap, O for overlap, and CGDO, that is capacitances for gate drain overlap. Gate to source overlap capacitance and gate to drain overlap capacitance. Now, these overlap capacitance like CGSO and CGDO are proportional to the width of that is W of the device and the amount that the gate overlaps the source and the drain. And these overlap capacitances of the source and the drain are often modeled as linear parallel plate capacitor. Next is, that is the source drain capacitance. Not only source, that is gate source drain capacitance. It turns out the fringing field lines and adds significantly to the total capacitance. And the gate to drain overlap capacitances are generally given as measured parameters in the MOSFET model. That is CSD, source drain capacitance. Next is source drain capacitance. That is for short channel devices, which may include the capacitances that exist between the source and the drain region of the MOSFET. The source and drain capacitance, which is denoted by CSD. The source drain capacitances in the region normally associated with the intrinsic capacitances, but it's still referred to as an extrinsic capacitance. And value of this capacitance is difficult to calculate because its value is highly dependent upon the source and the drain geometries. For longer channel devices, that CSD is very small in comparison with other extrinsic capacitances. And is normally that's why that this capacitance normally ignored. Next is junction capacitances, another type of extrinsic capacitances. Now, for that, first we have to know if a reverse voltage, we have to uh, recapitulate a PN junction, that when a reverse voltage is applied to a PN junction, then the holes in the P regions are attracted to the anode terminal, and the electrons in the N region are attracted to the cathode terminal, and the resulting region, which contains almost no carriers between these, and is called that region is called the depletion region, and this depletion region normally acts as a that region acts as a capacitance, and the dielectric of that part means there in the capacitor there is a plus positive side, and there is a negative side, and between them there is dielectric, and also this depletion region, which acts as a capacitor, and the dielectric of it, and the depletion region acts as a dielectric of the capacitor, and this depletion region increase if the depletion region increases in width, as a reverse voltage across it will be increased. If we increase the reverse voltage, then depletion region also increase width of the depletion region. Now, if we imagine that the diode capacitance can be uh, uh, like a parallel capacitor, then as a because the plate spacing, that is the depletion region width, increases, the capacitance should decrease. Now increase the reverse bias voltage across the PN junction, therefore decrease the diode capacitance. Here at the source region there is a source to bulk junction capacitance, that is CJSBE, and at the drain region also there is a drain to bulk junction capacitance, that is CJDBE. Now these junction capacitance can be calculated by splitting the drain and the source region into a side wall portion and a bottom wall portion. Next is oil bulk junction capacitance. If the MOSFET is in a oil, then a oil to bulk junction capacitance, that is CJBWE, that must be added, and this the oil bulk junction capacitance is calculated similarly to the source and the drain junction capacitance, and by dividing the total oil bulk junction capacitance into the side oil and the bottom oil of the components. If more than one transistor is placed in a oil, then the oil bulk junction capacitance should only be included once in the total module. Also there are some equations for the junction capacitances. But today that's all for today. That is different types of capacitances are there, extrinsic and intrinsic capacitances. And also today I have discussed about the threshold voltage of the ideal MOSFET. From that I have here we have done the calculation of how the threshold voltage can be calculated from this, and this is the equation. In next class lecture we will discuss about another topic on MOSFET.